Greetings, fellow mathematicians. Let's take a look at an example applying the ratio test where the term of our infinite series involves a lot of factorials. We're going to identify a sub n first, the entire term of our infinite series. And here that is n factorial squared divided by 2n factorial. And when we calculate a sub n plus 1, replacing all n's with n plus 1, we're going to have to be careful and use lots of parentheses. Now, we could rewrite that numerator, n factorial squared, as n factorial times n factorial, that same quantity multiplied out twice, but let's leave this as is and use parentheses. So we're going to replace all n's with n plus 1. And let's be careful and use parentheses around that n of the factorial in the numerator, which is squared. So we're going to replace and get n plus 1 factorial. That's all squared. And we're going to use parentheses also here. We're going to replace that n with n plus 1. All right, and we had our factorial on the outside of that. And now we're going to try to simplify this. Here there are no powers, so we can't use our exponent trick, but what we're going to use is the property of factorials that allow us basically to rewrite this and iterate it as the integer of the factorial times the previous factorial, where we subtract 1 from the inside. Now let's go ahead and apply that first to the numerator, which is, again, the factorials inside that square. All right, so we're going to apply our factorial property. N plus 1 factorial is n plus 1 times n factorial. That's pretty much exactly the numerator here, but we're squaring that whole stuff. So replace that. We'll get n plus 1 times n factorial. And that's squared. And what I'm going to do is distribute this 2 through the parentheses. And it looks like I'll be able to write my denominator, again, inside the factorial. Looks like I can write that as 2n plus 2, and then the factorial of that integer, 2n plus 2. All right, now if we were to leave a sub n plus 1 as this and divide, it's not obvious that anything's going to cancel. Now, you might be able to see, using exponent rules, you could square each of the quantities inside the parentheses of the numerator to get n plus 1 squared, and then n factorial squared. That would cancel with the n factorial squared in a sub n. But what about this denominator? Well, we're going to apply this property of factorials, but instead of having n in those spots there, we can apply it where we have 2n. So let's go ahead and take 2n plus 2 factorial, and we're going to apply this property, but to a little more general version where, again, instead of n, we have 2n. All right, now what that property of factorials does is we take that integer and then multiply by the previous factorial. We're subtracting 1 from that integer, n plus 1. n plus 1 minus 1 gives you n. Let's apply that here. So, applying our factorial property, we have our integer, 2n plus 2, and now times that integer's previous factorial, which is 1 less. 1 less than 2n plus 2 is 2n plus 1 factorial. What we're going to try to notice is we would like a factor to cancel 2n factorial. So let's apply our factorial property again to 2n plus 1 factorial. So we're going to have our 2n plus 2 there. And now if we apply our factorial property, we're going to have the integer 2n plus 1. And now that integer 2n plus 1, we subtract 1 to get 2n, and that's the factorial that we're taking of the integer 2n. So here at the end, we're multiplying by 2n factorial. Now this is not complicated, but you have to understand how this property of factorial works, and that's the key basically to this problem. So that is the entire denominator here. We've simplified that. So let's go ahead and write that. In our denominator here, we're going to write that denominator as 2n plus 2 times 2n plus 1 times 2n factorial. And in the numerator, I'm just going to take that outer power and square each quantity inside the parentheses to get n plus 1 squared. And then times now n factorial squared. That is most of the work for this problem. Now we just have to follow the rest of what the ratio test says. Next, we're going to take the ratio in absolute value of a sub n plus 1 divided by a sub n, and most of the work that we've done here should allow us to easily simplify that. All right, so let's take our time, take a look at the absolute value of a sub n plus 1 divided by a sub n. You can probably get a hang of the ratio test from here. We're going to keep a sub n plus 1 as is, so that result, which is a little bit long. So our denominator is 2n plus 2 times 2n plus 1 times 2n factorial. The numerator is n plus 1 squared times n factorial squared. And since we're dividing by a sub n, you know what to do. Multiply by the reciprocal. So multiply by 2n factorial divided by n factorial squared. And a lot of terms should cancel out. Looks like we can cancel the 2n factorials out. Looks like we can also cancel the n factorial squareds. And looks like what we're left with is basically some polynomial expressions involving n. And since we have factors n plus 1 and 2n plus 2 and 2n plus 1, n goes from 1 to infinity. So the absolute value here won't matter since everything inside is positive. And it looks like what we get for our simplified absolute value of the ratio is n plus 1 squared divided by 2n plus 2 times 2n plus 1. All right, and that looks like a very simple limit to evaluate. What the ratio test has us look at is the limit, which we're going to call L, as n goes to infinity of the absolute value of that ratio. So we're going to calculate the limit as n goes to infinity of this simplified end result. Numerator is n plus 1 squared, and then your denominator is 2n plus 2 times 2n plus 1. All right, now I'm just going to go ahead and multiply these out. You don't have to do that, but it's good to kind of connect this to earlier ideas in case the limits aren't obvious, especially if you're going fast during a quiz or exam. So I'm just going to multiply out both the numerator and denominator. We're still going to take the limit as n goes to infinity. And it looks like your numerator, if you multiply that out, or FOIL it correctly, you'll get n squared plus 2n plus 1. And if you expand and multiply out your denominators, looks like you're going to get 4n squared. Be careful and distribute correctly. Looks like you're going to get a 2n plus 4n. That'll be 6n. And it looks like you'll get a plus 2. And this one, you can apply L'Hopital's rule if you want, or observe here, you have the highest powers of n that are equal, n squared, between numerator and denominator. The limit should be the ratio of your leading coefficients 1 over 4. L'Hopital's rule also leads you there. Looks like we get as our limit here 1 over 4. And we do reach a conclusion with the ratio test. That limit is less than 1. And the ratio test tells us that our infinite series here, first, is absolutely convergent. And a result of a previous theorem says if your infinite series is absolutely convergent, that also implies that it is convergent. So that is enough work for us to conclude that the infinite series in question here, with a bunch of factorials, that is a convergent infinite series. This is a great problem. Looks very complicated, involving factorials, but the key here was understanding how we apply the iterative property of factorials, taking the integer and then multiplying by the previous factorial. Hope you enjoyed the video. I hope you're learning a lot. If you are, like and subscribe.